in this lecture, we'll be doing the problem and also the MATLAB simulation. Here we're going to take the same example what you had in lecture number 14, the pentagram system. So if you remember, we have the dynamics. In the dynamics state space, which was in state space form, A matrix, we had the B matrix and C matrix and D matrix. And the states to be controlled, theta x, theta dot, and x dot. Here use the force applied horizontal to the card. Theta is the angular position of the pendulum, x is the horizontal position of the card, and theta dot x dot the respective velocities of theta and x. The question is design a compensator here, desired to move the card by 1 meter while not letting pendulum fall. So it means theta desired to be 0. So in this objective, we can write theta d equal to 0, x desired equal to 1 meter, theta desired dot 0, and x desired dot equal to 0. So desired state variables, we can assume this is the desired state variable. So this is basically a tracking problem, we can say, because x is not 0. And closed loop regulator poles are assumed to be, these are the regulator poles for state feedback design, control design, and these are the observer poles to be maintained. Since the observer poles should be the faster than the regulator poles. So now we'll start the problem. So we'll go step by step how we can find the compensator for this particular problem. Solution. So here you're gonna use the separation principle. So separately design observer and regulator, and then combine them together. The same procedure what you have done in the earlier lecture, the separation principle. Now some step will follow the same steps what you have done in lecture 14 for finding the control gain parameters. Same procedure. What we have followed in lecture 14. Okay. So here, first we find the regulator control gain matrix. So first we'll find the regulator. We'll have the MATLAB code also for this particular example. Yeah, regulator control gain matrix. So here we have given, we can write the mat vector V, which contains the desired poles for the regulator, minus 7.853 plus 3.2528i and minus 7.853 minus 3.2528i minus 7.853 plus 7.85 ai, and the last pole minus 7.853 minus 7.853. Okay, this is the desired poles for the regulator. So we can use the command K equal to ACKER A, B, and B. And if you enter, so the mathematical things already have done how to find this K matrix. So you have to find SI minus A minus BK equal to 0. And we also can, from this, we can find the characteristic equation, and both will be compared. So from this V will be some form of characteristic equation, because there are three roots, sorry, four poles. So we'll have the order of the system will be 4, and we'll compare both the equation. We can find the unknown vector K. So, or you can use the MATLAB command here. This is the MATLAB command, which will give the K. So K found to be minus 1362 minus 909 minus 344 minus 313 is the control gain matrix for the regulator. If you notice here, the observer poles are same what you have considered in lecture 14, right? So here also we can form the yield matrix equal to minus 25149, and we can find the observer gain matrix 60 minus 183, 183, and 1810. This is, you can follow in lecture number 14. This is the regulator gain matrix, and this is observer gain matrix. So this is also vector, I can say, gain vector and observer gain vector. So now next part is, since xt is constant, if you notice xd, the desired state model is constant here. You can see it is equal to 0, 1, 0, 0. So we can find xt dot equal to 0. So this is also, you can write it as udxt. Hence we can write ad equal to 0, right? Ad equal to 0. Algorithm for the regulator problem. So now we have to find the feed-forward gain matrix KD. So finding feed-forward gain vector. So for that, as if you remember, we had the last equation in lecture number 5, AD minus A plus BKD should be taking to xt equal to 0. That's the condition we had, right? For this E naught dot equal to 0. So here we can write, so this expression already we had in the last lecture. So this is the condition for the compensator. So here we can write KD equal to, we can write KD1, KD2, KD3, and KD4. This is the feed-forward gain matrix or vector. So here BKD we have to find, because we have the BKD term here, right? BKD we have to find. BKD equal to, we can write, B is given to us 0, 0, minus 1, 1. So B is given to us here. This is the B vector, and into KD. So KD is KD1, KD2, KD3, and KD4. And from this, we can form a matrix, 4 cross 4 matrix, 0, 0, 0, 0, 0, 0, 0, 0, minus KD1, KD2, KD3, KD4, and the last row KD1, KD2, KD3, KD4. And another term we have to find A minus, let's now find minus A plus BKD. Okay, so let's find minus A plus BKD equal to, so minus A we already have my A matrix. This is our A matrix. The A matrix. Now we can find 0, 0, minus 1, 0, 0, 0, 0, minus 1, minus 10.78, 0, 0, 0, 0.98, 0.98, 0, 0, 0, and plus 0, 0, 0, 0, 0, 0, 0, 0, minus KD1, minus KD2, minus KD3, minus KD4, KD1, KD2, KD3, KD4. And we combine both the matrices, we'll get 0, 0, minus 1, 0, 0, 0, 0, minus 1, minus 10.78 plus KD, oh, sorry, minus KD1. KD1 and minus KD2, KD3, KD4, 9 plus KD1, KD2, KD3, KD4. Right. So now we'll find minus A plus BKD into XD. So here find now minus A plus BKD into XD. So this is already given to us. So XKD is given to us 0, 1, 0, 0. This is the desired state. And this matrix should be same as this. So here if you multiply, we are getting 0, 0, minus KD2 and KD4. Okay. So now we'll find this, we'll apply this condition. We'll use this condition. Okay. So now AD minus A plus BKD into XD. AD equal to 0 already have found. AD is 0 here. Right. So we are not, that's why we are not taking this into account. So equal to 0, equal to 0. And from this, we can find 0, 0, minus KD2, KD2 equal to 0. Right. So equation is satisfied by selecting if you select KD equal to 0. This equation only satisfies if you consider KD equal to 0. So we can write, let me define this equation number 1. Equation 1 is satisfied by selecting KD2 equal to 0. So in this case, since no conditions are placed on other elements of KD vector, we can take KD as equal to, we can write 0, 0, 0, 0. Right, this is what we have. Now we'll use the closed loop state equation, the closed loop state equation, which its rank is 2n, because we have the observer dynamics and observer dynamics state equation. So this is very, very important. We have done this part in the last lecture. So here, I'm not going to detail of it because already have found this expression in the last lecture. So here we can find ACL basically in MATLAB. If you write in MATLAB, we can write ACL equal to E minus BK. In BK, we can't write like MATLAB. We have to put star A. And second row, LC A minus LC minus B star K. So this is basically just star multiplication in MATLAB. Okay. So we can write, and BCL we can find B cross K minus KD, and there is only 2 rows, 1 column, should be K minus KD. So if you notice here, all the terms we have found, right? All the terms are given to us in this particular ACL and BKL. Only unknown we had K and KD. We have found KD is here, and K we have found before. This is our K is here. Here also we have found observer gain. So KL and KD we have found. So these are the gain matrices or vectors are here in this MATLAB code. So now if you find, so we need to find the eigenvalues of ACL. Okay. We need to find the eigenvalues of ACL. This thing. If these eigenvalues are negative, then we can say this is going to 0 over time. Let's now do the things. So let's check the eigenvalues of a eigenvalues of ACL. If you do in the MATLAB, you go right in MATLAB, and if you enter, we'll have minus 20 plus minus 20i, minus 10 plus minus 10i, minus 7.853 plus minus 7.853i and minus 7.853 plus minus 3.252i. So it means the dimension of a matrix, we can say 8 cross 8. That is 8 cross 8 actually. So that's why we are having 8 eigenvalues of Excel matrix. Now we are ready to simulate the program. We have found almost all the terms here. Now what we'll do is we'll find closed loop system SYS CL SS. We can put ACL, BCL, and C zeros, 1, 4, and D. So one, and also this is give you the state space model of the based on these matrices. And now if you find the output, so output, we know we can use the command ytx. This you already have done in the previous lecture. LSIM command, so SYS CL XT and T transpose. And if you simulate, we can find one thing we have to say here. Note that X vector contains the plant dynamics. There actually this vector we are talking about, this vector dynamics as well as observer dynamics. Here we can plot and see the results. Since if you go back to our problem, we want to see basically basically we want to see theta and x, because this is the condition here given. The compensator, when it is desired to move the card by 1 meter while not letting pendulum fall. So we are looking x and theta. So x and theta was main result we need to see, which can track the desired value x desired and theta desired. Right. So results for theta and x. So it means we need to see the, if you see the state vector x equal to, we have x, we have model like this, theta x, theta dot x dot. So theta x, theta dot x dot. So we want to see the result of theta and x in the state vector, right? So in that case, if you want to plot in MATLAB, we can use this command, plot t x 1 57.3 why? Because we want to, we are looking in the x vector first term, that's it is 1, and we are multiplying 57.3 because we want to see the result in degree. So 1 radian equal to 57.3 degree, and if you want to plot T X. So this is for card position, this is for angle. Now let's look the result, simulation result of this. So this is the MATLAB code. Dr. Prabhajit has prepared for it. He is very good coder. So this is basically the whole, whatever things you have done so far, this is the result. So if you notice, the pendulum already fallen, right? Because if you see, it is basically 90-degree falling. If you say 90-degree here, so it is 90-degree goes and again falling. So the design compensator is unsatisfactory for this particular problem. But the cart position has satisfied. If you look at the cart position, it is goes to the 1 meter. But the problem with the pendulum position by the angle. So there is a problem in this design, what you have done so far. So for that, only you can play on the pole. So we have to, the poles what you have chosen for the regulator design, we have to play something there. So this is the regulator part. So we have to do something here. We need to choose these poles, some higher values, so that we can modify the result. Or we can choose something new regulator poles, maybe very close to the imaginary axis. Also we can do, let's look how we can change the poles and how we can get some desired result for the pendulum and pendulum position. So now, so what we are doing is we are trying to move by moving the regulator poles closer to the imaginary axis, we can reduce overshoot. Yeah, that is very important. So we need to, because here if you notice, actually we have overshoot, undershoot. So if you want to reduce this overshoot, we need to place the desired poles to the close to the imaginary axis, which can increase the settling time. But if you place these poles towards the imaginary axis, there will be another problem will come. Settling time will increase. Let me write here. Overshoot, but at the cost of increased settling time. So it means we can't get both the advantages. We have to pay some cost for other case. So if you want to reduce the overshoot, if you want to maintain this angle bias, so you need to, maybe you can place the poles towards the imaginary axis. Maybe if you for example, initially the poles are here, and you are trying to place them a little bit closer to the imaginary axis. So in that case, we can reduce the overshoot, but settling time will increase. So it means basically we are putting more damping to the system. To actually damper, actually what it helps, it reduces this overshoot, undershoot, but settling time will increase. Right? That is the things we have discussed in classical control. So now we can choose the desired poles for regulator is equal to minus 0.7853 plus minus 3.2532i and is equal to minus 0.7853 plus minus 0.7 5, 3, I. So basically we are, if you notice here, we are just increasing, decreasing by 10 times of the discharge force. So now it is all in point, but if initially it's some number point, right? Yeah. And if you again do the command, k equal to, if you put like, so we can find V matrix, sorry, we can use V equal to, we can place all the 4 digit poles, this 4, this plus minus, you can put 4 poles in V matrix. And if you use k equal to, place command A, B, and B, will get k equal to minus 2, 7, 1.4, minus 5, minus 2. And if you use those k for this code or for the above analysis, we have the MATLAB code for that as well. So let's look. Yeah, we can see that now the angle is very less. So very less, that is overshoot, undershoot is reduced. Initially it was 90 degree close to, but now it is close to 5 degree. And also it is nicely reached to the cut position to close to 1, value 1. And here actually we modify the the pole, regulator poles, and this is the MATLAB code, you can go through it. And this is how we can modify the system response, and we can get our desired result. So this is what we have. This is we have designed the compensator for pendulum system. Now we are going to design the same concept for the aircraft system, and we'll see how the defined state in the aircraft can be controlled using compensator. So let's stop it here. We'll continue from the next lecture. So thank you.